All set?
So, should I use this microphone? Up to you.
I think both of them work.
Yeah, I think this.
I think you can walk around.
Yeah. Good.
I'm just trying to let you know. Yes, yes.
Okay. Hello everyone, welcome back from the coffee break. While we wait for people to trickle in, let me introduce Mark, our next and final speaker. So it's my great pleasure to introduce Mark Toussaint. He is a professor in AI and robotics at TU Berlin, where he leads the Learning and Intelligent Systems Lab, and he's also a member of the Science of Intelligence Cluster of Excellence. His research operates at the intersection of AI and robotics, focusing on how machine learning, optimization, and AI reasoning can be integrated. He is particularly interested in combining data-based learning with model-based reasoning for complex applications, including physical reasoning, task and motion planning, and robotic building construction. Very excited to hear what Mark has to share with us. So, Mark, please take it away.
Yeah. So thanks very much for the invitation. It's really nice to speak here. So I had terrible travel coming here, and so my slides are not so well in shape as usual, but I think they're going to be fine. I try to have my talk also a bit high level, so if you can also discuss it a bit on a high level, like I think topics that I find important. If you have some questions also in between, just interrupt and ask. So my plan for today is actually I wanted to talk about two things. One is being rational about investing compute. And I'll talk first about this in the context of planning. And at the beginning of the talk, you might think the whole talk might be just about planning. But then in the second part, I want to talk more about being rational about collecting data. And eventually, you will see also my point that at many levels, actually these two things I find are pretty similar. And also the challenges both pretty similar. So let me start first with being rational about investment compute when we talk about planning. So Valentin Hartmann, currently in Summit, he was previously with me in Berlin, was a PhD student. And that developed task motion planning methods, and this is just one video of his methods, the one with the state largest, where you see these robots coordinated to do some constructions. The work is cool. This PhD, the finished PhD was really cool. But that particular work, if you look into how was that realized and how much that, basically in the paper where we describe the method, we publish these kind of things. I'm not going to go through the pseudocode thing. The point is rather to discuss on a much higher level. It was rather cumbersome to come up with these arguments. And many of you maybe the work in planning, you know that it's not actually really hard. And it's also actually interesting to see in the older robotics literature, you find all of these papers in super complicated pseudocode. In the more modern literature, there's often papers without pseudocode, which is interesting, right? And they find this very cool. The question is, do we really manually want to develop these pseudocodes of algorithms? And that basically means that we as humans, as the AI researcher, actually decide on how the compute progresses, how the compute is being organized. And well, the gist is basically it would be great if instead of us coming up with these arguments, we would have the argument itself should actually decide where to invest compute. Right? It should really, basically be rational about how to solve the problem. To make this a bit more concrete, this was pretty abstract. Let me explain these class motion and talk in a bit more concrete way. So this is a search tree from one of our baseline solvers. The solver is called multi-line tree search. And this is a search tree which is very classical over actions. So this is the root node, and if you go to the right, so this is the whole tree actually, if you go to the right, this might be first action, second action, and fourth action. So this might just be 5 actions. Search tree over 5 actions. It's very small, you cannot read this. This is a zoom in, it's the same tree. So this is the root node, and gives 1, 2, 3, 4, 5 actions. For each of these actions or sequences, there is many things to compute in order to navigate and search through the tree, but there is a solution. You can, for every action, check if it's dynamically feasible. You can check if all of these actions get paired, whether the whole chain, like sequence of actions, is feasible. You can check whether there is paths, like RT trends, so between these in the schematic solutions. And eventually, you can also optimize the full path. So this is really a search tree for this class of problem. And the question is, how do we navigate through all of these possibilities of what you could compute where in order to most efficiently arrive at the solution? How could it be rational actually? Well, I mentioned like one method that we suggested in a second, but let me just mention in general like literature about this. So the solver has to decide where in the tree to compute what, and in order to most efficiently discover a solution. So actually there's quite some interesting literature on metavism, classical stage. So it dates like really back in the 90s, Stuart Russell. Stuart Russell had worked on so many things, but of course like this. But then there's also a couple of more modern papers, some of which also that are incorporated with, and also I think this one, there's also Aristotle Plus, I will mention it also later, which basically, do meta reasoning. They actually sometimes learn policies, or sometimes use other kinds of methods in order to find policy for research. We actually optimize the policy that searches a tree of the. And of course, this is also very much related to using bandits and confidence trees and multi-color research. And here in particular, I mentioned methods in existing research, which not only start multi-color research where you just do rollouts and just can do actions without any cost, but there is also some area of bandits where every call a query of bandit, you also have to pay some money for that, or it also takes some time. And there's an interesting literature on how to solve this. So basically, the theory, it seems, is clear. I mean, bandits or bandits with costs, with compute costs, or types, that theory is clear, and basically the question is how can you apply it to kind of automatically design algorithms to search for answers. Here is a little example. The point of this talk is not really to discuss the work, so I just want to give an example so that you can build on that. So you can actually now define another tree, which is the compute tree, and this is actually the decision tree, the decision of all possible computes you could do. So it's not anymore like these action decisions that we had before, but it's rather you can decide to compute the RRT of one of these things, or you can decide to compute the schematics of all of these actions, or you can decide to compute some other kind of like sub-problem of the original problem. Right? So that compute tree is actually much larger than the action search tree that we've searched earlier, because we have so many things that we could potentially evaluate and compute. But we can define it. And all of this compute tree now, so maybe I don't have to go into more details of what all of these things mean, but this is all the possible sequence of things you can compute. Maybe I should mention that the leaves of that tree are solutions. So if somehow you manage to go down one of these leaves and say, it's good to compute that means it actually comes. And here is a little paper, cooperation with Aristotle Plus, that we proposed the basic solver, heuristic actually to search over the tree and thereby automatically find policy that rationally allocates compute to search the tree. I think that piece of work was like a first little work which actually really tries to find rational policies in order to do research for class movement. But it was really just very basic. Now there is still ongoing collaboration with Stapas to make this much better, and also to, when I come to this later, to make it also much more data-based. And I also mentioned some other small pieces of work that we did on trying to be rational about positions. And that was another PhD student of mine, Joachim, that basically used more learning methods in order to first collect statistics about which of the subproblems of the overall problem takes how much time, what is the compute time, what is the probability of feasibility, and so forth, and uses these statistics to actually navigate better through decisions of the greater.
May I ask immediately?
Yes, of course.
We're talking about looking at all possible solutions versus it's the other extreme. Is there something in between? Can you find solutions for which means that, for instance, using research or something to benefit with a more long-term research?
Yes, this relates actually a lot to the second part of the talk. But if you're saying that the methods here that I'm discussing try to find all possible solutions, then that's totally true. And I'm very much like a defender of them. And also in the second part, I'm going to kind of like defend that. I find this interesting that methods kind of have a guarantee that they not only find one solution, but actually maybe with all possible solutions eventually. And they also follow the technique.
There must be a way somehow to improve our work based on the generate training for
Yes, exactly.
which is very limited.
Yes. Okay, this completely aligns with the second part of the talk. Cool. And I'm almost there in a second. So back to general view. So we would like the solvers, or we use actually AI methods for the solver to decide itself where to best compute, so that the solver can most efficiently actually discover a solution. Now the term in my discussion that I wanted to make is actually, this is a problem of information gain, not collecting data. And I think it's not so common that people think about planning like that. But actually planning is very much a process of data collection. During planning, you collect a lot of data. So this research, for instance, collects data about, in that particular situation, is this inverse candidates problem, is it feasible? Or is another one feasible? Or is the sequence of first picking this and picking the other thing, is that feasible? All of that is basically data. Right? And the planner is really, a means, to try to get information gain about these feasibilities out of data. And collect data that's what's feasible. And that's quite explicit in the multi-bound research that I described. I think that's also quite explicit in the typical upper confidence trees of research and of bandits, of course, if you think of them as bandits, but they're also at the same time data collection engines that are rational about how to collect data. But even actually I thought about it, and almost any planner you can think about, even if it's just gradients, and you think about it's a means to collect data. And I think this is a nice view on many things, on AI maybe, in general. And no matter what we talk about in the sense of planners or reinforcement learning, people think of planners being super different. They all just means to discovering the right data. For the planner, it's of course the data that first guides you, and eventually increase the solution. For reinforcement learning, exploration is an essential part that we discover before actually the prefrontal. I'll skip that in the discussion. But that brings me to the second part, which is about being rational about collecting data. In a sense, the first part was already about that. So people would usually look at it like that. This is efficient data collection. So the second part is a bit more explicit. And I'll start with something Eventually, I think I also, like a midterm or long-term goal is also to improve exploration reinforcement, for instance, but also exploration of other problems. But let's say exploration in the reinforcement. But I started recently actually to first think about generating diverse data in a different context, namely in constrained problems. So I hope that you know what is a mathematical problem, like a nonlinear mathematical problem. Right? It is usually we minimize some cost function f subject to constraints g and h, and in these nonlinear mathematical problems you typically assume that g and h are differentiable and f is just some cost function. Also differentiable, and then you can use whatever you like, sequential programming or maybe Lagrangian, whatever constraint optimizes. Now imagine that we have that setting. But instead of just trying to find one solution, what if we actually want to find all solutions of that mathematical problem? I find this a super important topic. What does that mean, finding all solutions? Well, let's say we turn it into a sampling problem where we interpret that the cost function actually becomes an energy, and then we define a sampling problem here where we want to sample from that distribution. Basically, so if the energy would be zero, it would be uniform in the physical space. Sample uniform in the physical space, or maybe with bias to different energy. First, I find this a super interesting problem and a surprisingly little literate problem. Here's a paper. You can look into the details. I didn't want to put too much into this presentation here, but just keep it short. In a sense, in that paper, I was just thinking about all possible existing methodologies that exist in Markov chain Monte Carlo, in robot-like exploration, like RETs and manifolds, in very particular like fields of sampling, like hit and run, which are actually polytope samples, but then also large amount of things, which is also Monte Carlo. But also in constrained optimization, and kind of like combine all of these building blocks of methodologies from these fields to just think about samples from these methodologies. And then these are just like examples. The examples from constraint problems. This one here. Last time I gave a presentation, somebody asked me about how fast it is. Like in the top or so, this is really milliseconds. Like you get very good, almost uniform samples in the physical space with a frequency of few milliseconds. That one here is actually much harder because the samples here are sequences of 4 frames. So you see usually 4. 1, 2, 3, 4. 1, 2, 3, 4. So these 4 frames is like one sample, and they're very hard to sample. I can tell you this was like a not fast motion then that's very hard. And this one is the frequency is just about every thousandth query or so, I get actually something like this only every second or so. Yes?
Immediately, if I look at that, first idea that came to my mind was my absolute research on investigating how many university knowledge solutions have. We're still doing that with the also last week of college, together with us for the farming arm, because they have for some reason 3 computers on my solution, for other reasons we only have 4, and I really want to plan a path where we have a homogeneous solution where we transition between users and solutions. So that would be an optimal solution to that problem.
Yes, and I think in some cases where you actually, when you talk about robot kinematics, like just the forward kinematics of a normal robotism, you can use other kinds of maths to actually get exactly optimal solutions to that. But I was clearly more interested in these kinds of problems like one here, where we have very complicated sequential manipulation problems, and we want to find samples subject to these sequential manipulation problems. And that's why I dedicatedly left this to be black boxes. So I don't really want to assume that it's 4 components and robots. It's really just as a mathematical program in very generic. Pardon? Yes, but you can form it in this context as a mathematical. Okay. Okay, so this is one piece where we actually, back to the story, being rational about generating data. This is being rational about generating data subject to constraints, and subject to a mathematical program for the computer. you might think this is pretty detached from exploration, reinforcement learning, and things like that. The point is actually that my hope is it's not, that it actually brings new ideas into that field. Not actually, as a exploration. So here's an example. Going at the end, you will see the application for reinforcement learning. But it's also following up on the idea that we use diverse optimizers that find diverse solutions in constrained spaces or large spaces. In that case, it's going to be trajectory spaces. And eventually, we will use these diverse trajectories that we find with diverse optimization to seed training of diverse policies in space. Okay, and in order to actually the optimizer that we saw here is like pretty conventional thinking. I did that, so constraint optimization, just a single point is being optimized. But there's also more modern things like Stein variation gradient descent, which takes whole populations that descend particles in parallel and thereby find other solutions. But they need a gradient, and in reinforcement learning we don't have gradients, so the question was what is an interesting diverse optimizer, particle-based, population-based optimizer, which is the free. And so Cornelius is a PhD student starting in that topic, and he was interested to try to have an evolution strategy version of standardization groups. So this means that we don't have hard constraints, but we have this energy function f, and we want to sample from that with the whole population. And the population, as we said, formally is kind of like levels. But we don't have a gradient of the energy. The normal Stein variation gradient set actually uses the energy, the gradient of the energy, so the probability, as the driving force. So there's a repulsive force and a driving force in order to converge the population to be against the estimator. And he kind of like translated this to become an evolution strategy by replacing every particle of Stein variation gradient set by a small evolution population. So what is usually a particle actually becomes a very small own population. And by using CMAES updates of a small population, you can infer what estimate what is the local gradient, and then basically do the same thing as Stein variation gradient descent, but with local CMAES pieces. A bit more efficient. You can read it. Here's some examples, only looking at the pictures. By the way, this is the ground truth, this is using the gradient, so this is not kind of forbidden. This is ours, not using the gradient, it's pretty similar to using the gradient, so that's good. And these are alternatives which don't use the also this is like an often cited version of OpenAI, which also doesn't really maintain by using. And we see examples which is about sampling points, but now also sampling trajectories. So we're getting into the direction where we use diverse optimization to define diverse trajectories. He also applied it to reinforcement learning in that setting though by using diverse optimization directly on the policy limits. And that also was quite robust because having a whole population of these policies, the diversity of the population is quite robust also religiously further learning. I skipped that actually because what I find more interesting is the second part. Instead of applying this diversity optimization on the policy network parameters, it's an interesting idea to actually think of it as being seeding data for policy investigation. So then you can just really diversity optimization. And this is a follow-up paper that we have a workshop version and a submitted version, so it's like pretty fresh. Where we use the exact same method to now optimize a diverse set of trajectories. It's 12-sum tasks. And then once we have these trajectories, we do skill training, so diverse skill training. It's a standard thing. I don't want to explain too much these equations here, but Domino is a standard approach which not only trains one policy but a whole family of policies, so it implies a whole set of policies. And they are trained to maximize diversity, so to lead to very diverse behavioral features. Diversity is measured really in the expectation of difference of features, in a sense. subject to being not too bad. And not too bad means not worse than, let's say, 80% of the best policy. That's a standard approach that exists already externally. So this is an approach to optimize a set of policies, diverse policies from scratch. And now that we actually have a method to find diverse trajectories beforehand, we can actually seed that optimization and help that optimization by injecting the data, the trajectory that we had before in the office. And that's the whole thing included. Okay, and as a result, again, this is the pure. So when we don't have any diverse data to inject into the policy frame process, actually, Domino is really elegant and cool, but sometimes doesn't work so well and so often. Anyway, so if you just apply Domino on many of the tasks directly, it's very brittle, kind of like, because the evolution of the data involved with reinforcement and all of this are also super wise. But when we inject the diverse trajectory layer into the batch, actually becomes super much. Here are these plots, which is diversity of the quality and how is this much more diverse with points. Okay, going back to the overall topic of this talk. I discussed two things: being rational about computer decisions, being rational about generating data. The first comment would be that I think I find it interesting that these two topics, which initially sound like super different, planning or reinforcement learning, I think are actually super related, right? Kind of like the fundamental thing of AI in general, which is that the systems are rational about gaining information, making decisions to actually gain information. And for both of them, I think actually in the first one, I think there is quite some space in the research, so things to do in terms of meta-reasoning, designing algorithms or letting that the algorithm design itself be subject to AI. And there is work there, but I think it's not totally not there. I think there is much more to come. And a bit similarly in the second, I think that the current ideas that are around, actually I must admit, like exploration and formulating made quite some progress in the last 5 years or so. There's steep exploration. Some things that I found surprising that we actually made progress with that. But it's still the same thing. I think in terms of the rationality of how to collect data, reinforcement is not really good, especially the reinforcement. And also there, I think there's lots of space for measurement. That's it. I want to thank you, and then also here's co-authors. If you haven't heard about this new German Institute of Robotics, you can also look at that. Just Google it. Thanks very much.
Thank you, Mark, for that wonderful talk. We have time for a couple of questions as we set up chairs for the panel discussion.
More questions?
Yeah, Chris. I mean, I guess robotics is in the name of the workshop. Like, so are many of these things robotics specific in terms of what they do?
That's a good point. So your question is, any of these are robotic specific, right? Well, yeah, that's actually super interesting because I think of them as being very, very much, but actually in their absolute form, they're not. Okay, why do I think they're very much robotic specific? Sorry, but a bit of history. So maybe 15 years back, I was also just working on generating market position processes, multi-canvas inference, and not really very robotic specific. So before I then started doing task and motion planning, which I think is very robotic specific. And I think one of the learning lessons that I had in task and motion planning is really the specifics of what are the challenges to getting content, to manipulate things, and eventually I ended up to capture all of this robotic specific knowledge in terms of constraining functions. And this is kind of like my personal. I think all of the robotics intuitions and understanding and knowledge we have, we can put into these constraints. And usually when I engineer these GNH constraints, they include content constraints, friction constraints, all physics, all types kinds of things you don't know. In a sense, therefore, like I think in terms of formulating these constraints, we can really look on robotics expertise and bias to that. That's why I'm also interested in Any more questions?
I like the term diversity, skill diversity. We call it skill disagreement. Where the idea was to use search development code that is we write and the sample states generated by a certain skill. But it was implemented, so in the end, we come up with some loss function that implements this idea of the skill activities.
You were saying the fundamental proof that's always very hard to give a fundamental proof of.
But in your approach, you show yourself.
Well, as long as we stay on just the diverse optimization side, once we leverage diverse optimization to see the scaling policies, so we lose guarantees again because we run into the normal, deep reinforcement things that sometimes works and not other parameters. But the diverse optimization, yes, very much, we have much better diverse guarantees.
And the metric can be reusable, so you have one for the business space, but in the universal skill space,
Yes. So that's a long story. Metrics of diversity. There is domain-specific ones, and I think in robotics makes so much sense to have metrics that are specific to contact nodes, in particular. Most important thing, interaction with objects, also in diversity in force space, for instance, which we haven't explored so much yet. But even if we are not domain-specific, just in the vector space, there is actually very I think many diversity metrics are misleading because they only measure parasiticity rather than measure the more global spread and discovery of nodes. The global spread and discovery of nodes is actually important than local parasiticity.
Can you explain in a few words how to see the policies from the trajectories? Like the policies are overfitted to those trajectories, or?
Yes. So this one. So you take domino, which is basically using deep reinforcement and training Q functions and so forth for this set of policies. So a set of Q functions, etc. But now you mix this with behavior cloning on the diverse trajectories. And so in every training batch, you basically do, I think it was equal, like behavior cloning on the diverse trajectories and in parallel that training of diverse states.
Just a quick highlight. You mentioned that there's not really much information have to go with it, there's not really data. And therefore planning and highlight on our direction. So in the last process, usually that you have more, right? So what is
Yeah, that's an interesting thing. So I also had this discussion once. I was in a model-based setting, and then I was saying I'm collecting data, and then people say, "Why do you collect data if you already have the model?" Well, but the thing is, I have a model. But when you have typically very often models, for instance, are forward models, like a forward model of physics. Right? But if I only have a forward model of physics that does not give me data about inverse, like solutions, for instance, like data about all the trajectories that you need to go. It's a bit like inverting a forward model or inverting a base model or something like that. And so in order to actually collect data about which of the things can be inverted or to which points in the future does there exist trajectory, I need to search that forward model, like this Motoko simulation or something like that. So even if I have a model which is a bit like a Motoko simulation, I still need to collect data about what is the feasibility distribution. And it's the same task and motion planning. I might have constrained models of what is possible, but to actually find concrete situations that fulfill these constraints is so to compute. And the outcome of that compute is the data.
I think we should get started with the panel. Maybe you can. All right, so let's thank Mark one more time. I invite our panelists to please come up on the stage. We have heard from some of them during the day, but I'll still do a brief intro for everybody. So we have Ben. Ben is a senior manager in the large behavioral models division at BRI, where he leads the multimodal policy learning and data team to create a general purpose robot via large scale training. Then we have Carl. Carl Perch is a postdoc at UC Berkeley and Stanford University, where he works with Sergey Levin and Chelsea Finn on training robot foundation models. He's also a member of the technical staff at Physical Intelligence. We have Yuki Nagai. She is a project professor at the International Research Center for Neurointelligence at the University of Tokyo, where she leads the Cognitive Developmental Robotics Lab. And her research encompasses cognitive developmental robotics, computational neuroscience, and assistive technologies for developmental disorders. And finally, we have Mark. We just heard from him. He's a professor at U Berlin, where he leads the Learning and Intelligent Systems Lab in the Department of EECS, and he's also a member of Science of Intelligence Cluster of Intelligence. All right, so we have heard different opinions and ideas of resource rationality throughout the day. So I'll just start out by asking what resource rationality means to you, and B, do even robots need to worry about resource rationality? Is it something humans can do for robots? So I guess let's start with Ben, and we'll go in order.
Right. So ultimately, robots ideally are a tool that actually does something that people care about. And so, this by necessity means that you're taking them and you're putting them into like real world situations where they can produce value. And any such situation is going to have constraints. So there may be the physical cost of the robot, there may be cost of people that are interacting with the robot or overseeing the robot, there may be R&D costs associated with building the robot or training the model, all of these things. And invariably, you will be more sensitive to some of these than others. But thinking about balancing them through the lens of rationality seems perfectly rational to me. And I think maybe the bigger question is just which of these costs scale with you, and which of them are maybe sort of fixed or transient. And I think that informs that, okay, as we're thinking about developing algorithms, what are the ones that are going to be persistent that are kind of worth tackling with more rigor.
Yeah, so I work mostly at Pi right now, and I guess at Pi we take a more industrial approach to robot learning, so we try to scale things up, and we try to collect a lot of data, train large models with it. And you may say that there we kind of don't behave very resource rational, and we're trying to just like throw money at the problem, but actually I would argue the opposite, that in these settings you actually care a lot more about being resource rational, because if you make like a 5% or a 10% difference on your learning efficiency, for example, it makes a huge difference, because there's a huge industrial operation below it. And so I think for us, resource rationality affects all the life cycle parts of training these models. So it comes down to what data should we collect. We don't want to over-collect because it's expensive. How can we train our models more efficiently? We have seen huge gains over the last year in how fast we can train our models and how little GPUs we need to use to do it. And I think it makes a big difference in the end of the day for our research iteration. On the robot deployment side, we haven't focused much on resource rationality, to be completely honest. Right now, most of our evaluations are run off-board the robot, so we don't care too much about how large the GPU is or how large the battery is that the robot has. And we can do that because right now we don't work with very dynamic tasks. So it's okay to have some latency and to have some off-board compute, and we do it in environments where we control the Wi-Fi and all of this stuff. But I would expect, as we actually want to deploy them into more and more uncontrolled environments, that this aspect of the problem will also give us more. And
So just a quick follow-up to that. I remember Ben also mentioned that a lot of data collection is art rather than science. So do you think that's a problem that we can just delegate to humans, figure out what's the right way to collect data to make it more efficient, or do you think that should be automated?
So right now it's mostly in art. It's basically Chelsea sitting down at the beginning of the week and choosing what data we collect on what tasks. It's not very scalable, like at some point even Chelsea will struggle to have all the tasks in her memory and decide what is still missing. And there's much more granular stuff you may want to decide on, right? Like the task is a very abstract thing, like it's a very high level thing, but maybe you want to collect more data with certain types of lighting conditions, or with certain types of robots, or certain types of particular objects we don't have a lot of data with yet. And so at that level of granularity, no human can keep all of that in their memory, and so then you need automated approaches to surface where your robot still has lags of experience. And that's a research problem. Like we don't have great solution right now. It's very heuristic, but that's definitely something that would play a big role.
For my research, resource-based learning is very crucial and one of the key research questions. The reason is that my research lies in the intersection of the robot learning and the child learning, human child learning. And then as we know that the human children have a lot of limitations. We call it the maturational constraints. They have the limited or immature sensory abilities. They have limited memory capacity, and also their environment. So that try to scaffold such a maturational constraints. And then we often ask them how this maturational constraint can really help the child development. Why children needs to have such a maturational constraint? Why the children are not born with a matured mechanism? And then we learn from the child study that such a constraint can actually facilitate the learning. For example, with their immature, the visual perception, they can more easily extract more important information from the visual, and also from their limited motor capabilities. They can start with a very small exploration areas, and then gradually expand the areas for the exploration, which also facilitate their learning. So then we try to integrate these ideas into the robot learning in order to see how this mechanism can also help the robot learning. And by constructing such a computational model, we can better understand the human limitations again. So for my studies, very, very key research questions. And then, although we did not utilize resource rational learning in our community, we often say developmental learning or maturational constraint learning, but we found that it's very closely linked with the theme of this approach.
So I want to poke that a little bit. So it's interesting that you said constraints help learning, whereas I think in robotics we often believe that we should collect the highest quality, highest fidelity data, right? So do you guys have thoughts on, what's the rationale on, I guess, human development side, but is there an analogy we can draw in robotics as well?
Yes, and I also remember the one good example that there are some persons who have intellectual disabilities called Savant syndrome. Savant syndrome is also linked with the autism spectrum disorders, and they often have a very superior ability. They can remember what they have seen, or they have a photographic memory, and they are very good at remembering all the calendars or the dictionaries, but then they are lacking the ability to do social interactions. So we don't know yet how this superior memory capacity can really help their intelligence, but also it hinders in acquiring social intelligence. We try to understand how these two abilities are really linked. In one direction, they can show the very optimal behaviors, but in the more social direction, they often show the difficulties. So we think that there must be some link between this motor learning or behavior learning and also the social capabilities. So that is, I think, one interesting point to be also linked with the robot learning, which aims to achieve the optimal solutions, or we also think about integrating such a resource-based learning.
I I think in my experience, there actually isn't a tension there. Like people like to talk a lot about data quality. I think that's true in robotics. But I would say there's maybe less agreement on what high quality data is or it means. And I've definitely come around to the camp of don't make things too easy for your models. And that's especially where kind of thinking about the training life cycle and phases I think is useful. What you want, when you're doing post-training is different from what you want in pre-training. But actually, we've seen that if you add like auxiliary tasks, so you make the problem harder, and potentially actually your losses get worse, like the model is not fitting it as well. The representations you learn and the final outcome actually can be better. And there's even some really cool work that's come out in the last couple of years that shows there's some tension between in-weight learning and in-memory learning or in-context learning emerging, where if you have a little bit of, let's say, noise in your labels, or the same input can map to multiple outputs, so it's not quite a function. Like that sort of thing actually incentivizes in-memory learning. And I think it's I'm not an expert in human development, but it sounds like there's some parallels there as well, where if you think about what makes a good education program, it's not something that's too easy. And even if you want somebody that's good at a specific thing later, generally you want them to have a challenge and fairly broad education program. And I see some parallels there for sure.
Okay, back to the original question. Okay, I think the original question was would robots need to be rational, essentially, right? I would really distinguish between whether you think of a robot as a product and you're maybe a company or so, and it just wants to get things to work. And I think in that case, maybe the robot doesn't have to be rational. If the company has enough money, then maybe also the company doesn't have to be so much rational. And just collecting lots of data. And I do believe that actually will carry very far. It might actually be the rational choice for the company right now, because it is the most promising. But from the AI science or research perspective, I find this a bit sad actually, because even though that this is the way to make things work, this doesn't mean that it's the most interesting science. And I think sometimes I find it also in our community, it's sad that people always eventually say, yeah, but it works. So, but only because things work is not how do I put it? So it doesn't mean that it's the right thing or the right kind of thing. So I think from the AI science perspective, thinking about also making data collection and resource use, all of this also subject to AI is super interesting and important for science. And I sometimes feel that this might go apart because the companies are so strong in getting things to work and kind of overshadow all the nice other kind of research that I find is super interesting. Maybe a point about what is the optimal data, that is actually what's interesting, because the economists will be interested in learning. So I totally don't have the answer, but I find it also super surprising that there is so much effort into large-scale data collection that we don't actually really know how it should be structured, what it should cover, and what is really good data. There's so little theory in fields on what is good data. And I'm curious, maybe also how you actually see that, because all your business model is basically built on collecting more data, right? But don't you worry that you don't really have a theoretical foundation? So what actually is the data that should be collected? Or we have a clear idea of it?
I completely agree with you. If companies had a lot of money, there was no limitation in the budget, maybe they don't need to care so much about the resource-based regional learning. But then I'm also working in the human-robot interaction communities, and then the researchers aim to develop a robot who can interact with their human partners. But then the human partners are quite different. We don't have an optimal way for the communication. The robot has to adapt their communication abilities to the different persons. So in that case, we cannot collect their unlimited the data for one person, for each person. So in that case, the robot has a quite limited numbers of the data for learning, and then so it must be the ratio for the learning. So it really depends on what kind of task researcher will target.
Yeah. Well, I mean, I think, as I had said before, I don't think anybody is happy with the state where we just collect data based on heuristics. And I think we clearly all would prefer a solution that maybe you wouldn't call a theory necessarily, but at least some, more intelligent way to decide what data is being collected. A theory assumes that we exactly understand maybe how the learning process leads to generalization, things like this. But you can also have a more, more advanced way that is still somewhat empirical, but it is at least guided by some metric of the pulse's performance and intelligently chooses what data is missing. Right? So I think that is very much something that could be beneficial and that I think people want to do research on. I think the practical challenge of this right now is that the only way to do that kind of research is through a lot of evaluation. Right? So basically the cycle of how such a research project look like is you choose a split of your data, you train a model, you evaluate that model, and do that many times so that you understand empirically how does the data actually impact on performance. And the main bottleneck for that is the evaluation model. People have done this work for language models because there's a fairly good proxy metric that people have developed in language modeling, which is something likelihood complexity metrics. But in robotics, those don't work. You cannot look at loss curves and tell you whether the policy works or not. You do not have an offline metric. And so running a lot of online evaluations is currently just not practically feasible. And that's why, even though many of us think we should develop better intuitions on this, and we should develop an empirical, at least an empirical understanding of how to steer data collection, we cannot currently do this research because we do not have the offline metrics to actually run. But yeah, it's still an empirical science in that sense. I think a very theoretical understanding of how the data influences the learning and generalization is not just missing in robotics, it's like missing across most fields of larger scale machine learning systems.
Ben?
Could respond, but
Yeah, I mean, okay, so slightly opinionated take that, but I do think that there's a dangerous middle ground where you can fall into a trap of really scaling up data collection in what I would call sort of semi-toy environments. Basically, you're constructing the data curriculum to collect, and it's a dangerous place to be right now because there isn't really a theory of what data is good data. And because it's relatively expensive to do this, so you can't just cover the space of all possible about data. So you have basically tiny samples that you're drawing from what the population across the world data would look like. And I think one way to do this is sort of mechanistically get a better understanding and then start to do targeted stuff. I think the other avenue though, which just it feels like it's time, is really lean into getting robots in the world. And I think over the next couple of years, to the extent that we're going to start to have data sets that are like more useful, I think a lot of that is going to come from robots being put into things that are more like production settings, solve real problems. And in the same way that a lot of the successful language models, it came from the internet where there's a lot of data of people doing stuff that they found valuable. I think that's a much easier direction to work from, that's much better understood, and trying to kind of bootstrap the construction all the way.
I guess I'm just surprised no one has mentioned reinforcement learning at all in like the last 10 minutes of this conversation. The second part is it explores. That's like part of the feature of reinforcement learning. Any thoughts on that?
I think that's telling. it's telling that reinforcement learning hasn't been the most emphasis in really exploring on that large scale as data sets that we're currently collecting all possible skills. It's really big. So I think that's the reason why we're doing so, but that's why this invitational approach currently is really stronger in the kind of skill and the breadth of skills that currently people want to see in robots. I think that's a good point, right? Because it shows that there's something missing, because this autonomy that we were hoping about reinforcement eventually we discover anything in that space of possible robotic behavior that we mentioned, which I find really interesting. That hope is still there, but we're Currently, at least what they wanted instead of just collect data mining of computation.
Okay, that's right.
Also, the space of robot behaviors you mentioned, maybe could you sketch that space?
Let me push back on we are not doing RL because we've been invitational sort. I think like RL from scratch is not practical in real world settings, at least today. You can push back if you want. I think the reason we're starting with invitation is because to make RL practical, we need a model that is good enough at exploring the world that it actually can learn within a time span that is feasible in real world environments. So it's not like we're not doing RL, but we need a foundational model that is strong enough that RL is feasible.
I mean, I think that's right. And maybe the short version of like, what is the manifold of all possible robot behaviors, or what is the space of all robot behaviors? I have no idea. I don't think anybody does. I think you can't write it down, and that's actually to Carl's point. The only way to really get that seems feasible to me is basically data driven. And supervised learning doesn't completely solve the problem, but if you can bootstrap, if you can get robots doing useful things, and then you can use that to start learning that manifold to explore on with something like RL. That seems to me the sort of only viable avenue that we've seen so far. And I think locomotion was this like really beautiful special case where if you look at the action space and you do sort of random stuff, you can actually start to get signal relatively easily because you fall forward and that's great and you follow the gradient. But think about sort of moving your own body arbitrarily, and your job is to set the table, and like how many random actions might you take before you make meaningful progress on that specific task. And doing any of it from scratch is just incredibly cool.
Again, they're inspired by their developmental sciences. I think they're like a limitation of the motor capability or sensory capability in the children already somehow constrain the exploration spaces. So even if the robot or the children do not have like training data from the beginning, but then their limited capability of the sensory motor system already somehow constrain their exploration experiences, which actually naturally lead to their resource waste. That might be their one interesting idea which I would also implement.
A quick comment again about the space of possible behavior system. Right? The danger of sounding like the old guy and so like old-fashioned roboticists, so they would say they have a pretty clear idea, or not clear, but at least an idea of what that space looks, and that's very much dominated by physics, by physics priors. And, there's always talk about priors. And I think your statement that, well, it's fine if you say you don't have an idea of what the space looks like. The statement that we would have no idea what the space is possible, what experience looks like, I think that would be disappointing. And also the statement that we can, and that's why we only rely on purely data-driven methods, is also a bit disappointing because it would mean that all the understanding of robotics and physics and context and all of this would be useless.
So I think that might be true. I think physics and our own priors, they're great. There's clearly a lot of information in there. I think where it can be a little bit of a trap is like the stuff that is obvious to us, that you think to write down, and you think to encode into a physics prior, it's so ubiquitous that that's like the first stuff that you actually be learning in data. And what you really need the data-driven stuff for are all the edge cases that are complicated, that are hard to write down. And currently we don't have a better solution but to scale in order to learn that hard stuff. And just on the way, you sort of incidentally learn a lot of easy bits. And like one version that we saw with some of our first big foundation models that were really terrible. Like they didn't work very well at all. But we started learning like pick and place priors, like just super fast. It starts to servo only towards objects. It seemed like some notion of objectness was emerging. Some notion of retrying when you drop something was emerging. And so like I do think there's a little bit of a trap where you're like, I know so much and that's really useful. But often that's the stuff that you sort of get along the way.
One comment to that. Do you believe that the representation was learned is strong and more generalized? For instance, if you would attach some particular tool, spoon or something to your system, would it have understood the concept of pick and place, or is it just a solution to this particular hardware system?
I I mean, if your data comes from one hardware system, you're not going to generalize completely outside the support. But I think the point is that before you get enough data to solve all of the stuff you care about to make it useful, like you'll get that piece. So if you want to use it like a new type of hardware, for instance, long before you're getting like dynamic sort of high performance dexterous behavior, you'll start to learn basic pictures behavior. And we've seen this too, even just at relatively modest scales, combining like OXE and droid data, that sort of thing, with data from different robots. It doesn't take a lot for these really simple things. If you can think of putting, like, let's say, in the action space, you kind of start to get a lot of that pretty soon for free.
All right. So, did you want to respond to that?
To the earlier comment.
Sure.
Okay. So one comment you had is the prior that things about physics is also kind of like little information that would be the first thing that the system can know. I had this by a couple of times from students too about this, like that they simplifies, that would be the first thing. And I find this a super interesting comment, and I really want. So yes, I mean physical equations are like pretty concise, pretty little. You can think of them as being very little information, right? You can even write them down in just a line of code. Not code, physics. So it's actually not so much. Actually. Also in terms of information. But if you think about what can come out of physics, the world is like super complex. Right? Although like this physics, there is also super simple equations. The things that can come out of them are super complex, like life, universe, matter. I don't know about all of this. And so, although the fundamental equation might be so little information that the system could easily learn and maybe forward equations, but it would not at all be easy for systems to learn all the patterns or things that come out of these equations. And maybe that latter part is the actual thing that the deep model would have to learn. And so when we say something like we should explore physics prize, it's not about that we should learn a forward physics equation as in the textbook, which is smaller. But rather we should learn the kind of patterns that can come out are feasible under physics, can exist under physics, like behaviors that can exist under physics. And that's super complex. That's just as a reply, say that would be the easiest thing to do.
Moving on a little bit. So my next question is about the idea of using multiple resources. Right? So during the workshop today, Yuka mentioned the idea of a data pyramid. So you want to learn from human videos, then you want to add some simulated data to that, and then you want to collect some real world data, right? I believe you guys are primarily relying on human demonstrations, right? And we also briefly discussed the idea of using RL to fine tune a large model that was pre-trained using demonstrations. And I believe Mark here really believes in using physics-based priors. So these all sound like hybrid approaches which are mixing different sources of data, right? What do you believe is the right hybrid solution? Maybe the best solution is not hybrid. That's up to you. And B, how do you even evaluate the resource rationality or efficiency of these hybrid systems, because they are using multiple sources of data, so how do you even measure them?
Okay. Yes. We're trying to use different sources of data. I think there's trade-offs for different sources of data. There are some sources of data that I think people are very excited about, that maybe it's less clear to me why. For example, simulation data, which I guess is somewhere in the middle of UK's problem, I think. So I think there's trade-offs in terms of like how much data can you get, how diverse is that data, how readily available is that data, versus how much signal you get from that data for the thing you actually are trying to learn, which I guess is maybe the action behavior of the robot here, controls. Maybe a trap that we can fall into is that we're trying to optimize this mixture in a setting where we have a very different distribution of some of these data sets than we would have in the final solution. So to give an example, I think people are excited about learning from human video for obvious reasons, but then a lot of the experiments that we run with human videos are typically in a setting where we have very, very little robot data. Maybe we collected robot data on like 2 2 free stations all in the same scene, and then we show adding human data now helps generalization. But we make these conclusions in a setting where there's unnaturally little robot data. And so the gains that we see may not actually be gains that we can realize when we train it in a setting where we have more reasonable amounts of robot data. So, you know, we would like to figure out how to use these data sources, but I think we need to do it in a setting where we have a realistic distribution of the other data sources that we're trying to correlate.
Again, from their quite different perspectives there, because so we are mainly focusing on the learning through their interaction, learning through the social interactions, and then we also design like a human-robot interaction scenario where the human partners are supposed to teach something to the robot, for example, the object manipulation and so on. And what we found regarding the data types, what we found from this human-robot interaction and also the caregiver-infant interaction in humans is that the teachers tend to exaggerate their teaching behaviors or sometimes their languages, which is actually quite different from their current robot learning system. I think that when you are working with their imitation learning, their human teachers are supposed to show their optimal way of the object manipulation, for example. They don't supposed to exaggerate their behaviors. But interestingly, in their caregiver-infant interaction and also in the human-robot interactions, the teachers start exaggerating the object manipulation. For example, that if you're supposed to teach the object replacing from here to here, maybe you will show this the most efficient trajectory to the robot in order for the robot to learn or imitate this exactly the same trajectory. But then when the teachers want to really facilitate the learners' learning, they started exaggerating, picking up an object and then putting down. It's somehow like showing the action primitives in a more natural way, although they are not taught to show in this way. But then from the observation, we found that the human teachers naturally start exaggerating their emotions. I think that this is very interesting phenomena which can be also again integrated in these robot learning communities, because although I know that many researchers are working in the imitation learning, but then their teachers are most cases are like optimal teachers, very well designed learning patterns. So, but then if we again get the inspiration from their human interactions or human learning, we can still implement many interesting ideas into learning. How this exaggerated demonstration can really facilitate robot learning the action primitives or optimization of the trajectories and so on and so on. So I think that is one interesting point there regarding the data types for learning.
I have a super small brief comment on that. We often think of the data as, in particular in imitation learning, as positive examples, right? But actually from how many pieces of exploration and so forth, we very often know that actually data, the purpose is information gain. I said it in the talk, just repeat it. And that very often also means that it should be like negative data or data that is really just explorative in the sense of gaining information, not of value and so forth. And I have no idea what that would mean for training the models and so on. I would find it interesting, but somehow I think data like that is awesome.
Basically what Ben said earlier. Like we said, we want different types of data for example, pre-training. That we want to teach the model a general concept of how to interact with the world versus the data that we're currently, I guess, using post-training. We're trying to optimize it for a specific task. And so similarly, if you want to teach the model to be good at exploration, probably you want very different data than you want if you want to teach it to just solve one task.
I do. I think I have a magic insight to add, but I do think that this question is super important, and it's maybe a little bit of a unifying thing here. Like this is the sort of quite literally like multi-billion-dollar question. Is the opportunity cost is really high, and it basically like getting stale. If you're going all in on millions of hours of video, for instance, just the compute costs of deciding to ingest that. If you're collecting it, the cost of instrumenting. it's high. And so I think this is where even companies that are operating at more scale, you are very sensitive to opportunity cost, because if you go all in on data, on one modality of data, it's another way that you decide which data you collect. And I really hope that we can build a more theoretical understanding. I think being able to model out, okay, if I allocate this much effort to collecting this type of data, here's how I think my performance will change in a specific regime. Language models are one click ahead. There's some fuzzy understanding that's coming into play, but robotics sort of needs it.
So I guess that was related to the question that I had real quick. All right, maybe those sections in the microphone. Like you talked about information gain, so it's one root of this. It's kind of, in fact, to the resource rationality. It's information gain divided by cost. So maybe whatever is the best form of that function is distributed to be what we want. So what you mean? Because you were talking about like opportunity cost, but didn't know if you kind of mean dollars in that case. Maybe some kind of understand a function of trade-off between like cost to collect that data versus information gain to collect that data.
Yeah, or you might even just say robot performance, or maybe even in particular like utility, whether it's to you because you're solving your own problem, or to the customer because you're solving a customer's problem, and how much better do you do in the ways that you care about. It's not just monetary cost. I mean, that's part of it, but even like a well-funded organization, you only have so much bandwidth, and you're allocating how you're going to spend R&D time. You're potentially deciding what strategic partnerships to engage in. There's a limit to how many of these threads you can do everything at 110%. So beyond just the money, sort of general resourcing, you do ultimately have to kind of decide how to balance the portfolio.
Do we have questions from the audience? I think we have time for a couple.
One comment that we did not talk much about this. So engagement of a strong selection mechanism. Our algorithms, they don't die out, but maybe they should die out. Maybe we should talk about risk as well. Maybe there is some channel learning algorithm that could substitute all your effort between now and 5 years. Do you think in 5 years you would give the same answers as today?
Hopefully we'll figure out something better. I guess currently the strategy is to basically try to understand where the current paradigm leads us. And if we encounter roadblocks, then we'll figure those out. But I'm not sure whether the potential that in 5 years what we do today is wrong should overrule, starting that path. Because maybe we need to start that path to actually figure out whether or not that's the wrong way. Otherwise, we will all just guess. Is that the right area? Is that the right area? We should actually try it.
I mean, the steam engine is pretty obsolete now. Added a lot of value to the world.
So maybe going back to, you made some of the earlier comments that a differentiation between like training for rationality versus enhanced cognition, and whether or not that's a thing we should actually do. Because, for example, a lot of things that we do, like some problems are much harder to figure out than others. Sometimes there's a trap in training instead of like pre-plan. Does that factor in? Maybe some of the ways we have designed the models, maybe if we're putting way too much effort into training time, it would be better to collect some local data for that task, or actually reduce overall costs, I guess, of resource usage.
I think that's an interesting question. I think a reasonable thing to do is to try to figure out which of these scenarios are very common, so those who try to distill into the future. So that you essentially amortize the thinking process into how we act with policy for all problems. But then it's making it efficient to do it for all problems. And so if we have the ability to spend inputs from to improve generalization on long-tail problems, that's reasonable. real world problems also have an inherent inference budget. Certain problems you need to act fast, as opposed to you want to distill people for
Yeah, but I get that point as well. I guess it's sort of the other side. I mean, we're trying to reduce the cost of spending machine learning tests. So it's not having more compute at that time. Like most of the time, we're not really thinking about it. At least that's what it seems like for most of the students in the application. And that may be even connected to your comments too, but like how instructors exaggerate things. Is that they doing that in order to like make it like it's something they think, or is it also to help get the attention of the people that are actually trying to watch at the same time, or whether or not like these over exaggerated resources that the teacher is doing is going to convey more information to the person as well as keep their attention. Process. But then one back to this is just I guess I don't see it wasn't necessarily about adding more test time compute, it was really just reduce as much test time compute that ever is needed in this process. Like most of the time we don't need to do a lot of compute. We tend to make our biggest model possible such that we know we can always have enough compute for the hardest problem. And instead of just having some version that's very small and then building like under the wall at the time, instead of something more complicated. Spending a lot more time thinking about real-time reinforcement solutions.
I can see test time compute happening live here.
What was the question? I didn't what you said. I'm not sure.
Yeah, I guess is there a different version of this out there? Instead of having the biggest model always, we're currently use for basically everything, including this having a move after gravity object. Is there a way to do this adaptively? Much more
So this is not actually how language models work. You train a big model and then you distill it and you use it to synthetically generate data, which you use not to distill. So in language model, we actually train big models and then make them smaller. We don't do it in robotics yet, but we distribute them. Like right now, we don't see benefit of making the model much bigger. Our current learning paradigm does not benefit from a much bigger model, so we don't. But ideally, we would want to figure out the paradigm where it does benefit the performance to make it bigger, and then we can make it bigger and still get that.
So you don't see any technical issues there.
Like in robotics, we have fundamentally harder inference constraints than any of the language models that has. So there will be fundamental issues for each where we need a model architecture that allows you to run even faster or faster language models. But the principle of distilling a larger model into a smaller one, I'm not sure how it would be defined in the language model in robotics. I do find the comment about exaggerated movement very interesting. I'm trying to understand why. Like maybe one reason why people do this is because you want to present a pattern that you want to teach in a way that is the least confounded with anything else that you could try to teach. So you like show the pattern very obviously in a way that is not natural. So that the model, which is the child, understands that this is the pattern that's supposed to pick up here. And I guess the way we're currently collecting data is not teasing apart patterns that we want to teach one by one. Maybe that's a more efficient way to teach it. It's not something language model people worry about because they don't design the data, like the data exists. But if we collect the data, then maybe this is something that we should actually do.
Right, so we're already running more than 15 minutes over, so one last question to wrap it up. What is one problem you think students or researchers should be working on today that's going to be most relevant 5 years from now for robotics? And which you think not as many people are working on it. So you want people to work on it more.
I said already diversity. There is already more people than
I think that this field, their progress is very fast. Actually, this is their second time for me to attend for conferences. The last time in 2019, I actually gave a keynote talk in Osaka, and I see the very big improvement in the learning mechanism. So it's very, very challenging to really follow even there, not only developing something new, but then follow up is already very challenging. So I think that would be the important challenge for these topics.
I'm not sure that I'm thinking about a 5-year horizon, but I do think that a very important problem to work on is to try and understand how we can measure performance without incurring the cost of running a lot of real-world robots. This is a thing that would be very useful even today, but I think it could be a problem hard enough that it may take a few years to actually figure out how to do this work. But I think it will lift many boats from very practical kind of company concerns to more researchy concerns on trying to understand how different method solutions influence model performance. I think all of these things would get unlocked if we have better ways to understand performance without needing to run the robot all the time.
One follow-up to that. So I think classically the way people tackle that problem was you have a model, you run evals in the model, and I guess you plan that so that you take better decisions in the real world. So are you thinking along those lines, like learning a model, building a model, or something else?
I mean, I don't know whether I have a favorite solution, but that is one solution that we could, I think, explore. But you could also just have a way to look at the weights, or a way to run some often involves on existing data sets. There's many ways to try and test this model. And I think figuring out a way to do this well is very important.
So strongly second the eval thing. I think there are a couple of plausible backup plans that I would love, innovation to make things faster. I think one plausible backup plan is just large-scale deployment is enough to both scale some of it in a wild eval, but also bootstrap their models, become better for evaluation. That's sort of a brute force thing, but there's reason to be hopeful if we don't get something more efficient in the time. I think also there's some reason to be hopeful that potentially as the data diversity grows and the models become more sophisticated, that offline metrics start to become more correlated with performance of the seek, but it may happen. Putting all of that stuff aside, and this is maybe even a little broader than just robotics, but I'd say meta learning more broadly is, I don't know if it's underexplored, but there's been this really beautiful progression to a better lesson convert, where first you think a lot about kind of engineering everything, and then for a while we were engineering features, and then that sort of fell away. But there's still a lot of stuff that we do have engineered, and data curriculum is one of them actually, but there's a ton of stuff. Your architecture choice, even your choice of supervision signal, there's a huge space of things that we're currently hand designing. And look, I'm not saying we should throw away all of that structure instantly, it's serving us well, but there's clearly a frontier there where some of these are going to become bottlenecks sooner rather than later, and I'm very excited for the next wave of research, allowing us to take data-driven approaches for some of what we're doing right now.
Right. Sounds wonderful. Let's give a warm round of applause for our panelists.
And just some concluding remarks. Thank you all for attending, and wonderful thank you to our speakers and our panelists, our contributed talks. Thanks for making our workshop a success, and wishing you a great rest of your day. Thanks very much.